For last few lectures, we are talking about linear solvers. We have talked about two types of linear solvers, direct and iterative. In case of iterative solvers, we start with an initial guess and then we keep on updating the guess. And we hope that eventually we'll reach the correct solution. From this initial guess to reaching the correct solution, this is something we call convergence. If the solution reaches the correct solution, then it called convergence. But how we are sure that in iterative solution our initial guess will lead to convergence? That is always a question in iterative solution, and that is something we'll discuss in this lecture. Recall our discussion on the theory of iterative method. Let us say we are trying to solve for u from this linear system AU equals B. In iterative method, we break this A as E plus F, where E is some sort of an easy matrix that we can invert easily. So we write this system AU plus B as EU plus FU equals B, or we take this F to the other side and we write this E is equal to minus E inverse FU plus E inverse B, because E is slightly easy, so we can invert it relatively easily. So essentially we come with this algorithm U equals MU plus C, where M is this minus E inverse F and C is E inverse B. So we have unknown both sides, left side as well as the right side. So what we do, that we assume that, well, we know this U naught, that is our initial guess, and we put that initial guess on right hand side and we calculate U1 from the left hand side. So essentially our algorithm comes as UK is MUK minus 1 plus C. K minus 1 starts from 0, where I put the initial guess. So this is the theory of iterative method, and we hope at some point this UK, as K grows, at some point we will have a reasonable solution. But are we going to have a reasonable solution? That is the question we will ask now. Let us say that the exact solution is U star, and we somehow know this is the exact solution of this system AU equals B. In that case, I can write AU star equals B, and if I take this again, A, I break it E plus F, and I take other side, the M goes other side, but U in both cases, left side, right side, are U star now, and we are pretty sure that this is the exact solution. So when the solution is exact, then this is U star equals MU star plus C. This is the relation. Now, after kth iteration, we have some value of UK. This is not exact, so we have some error after kth iteration, and that we are writing as EK. That should be whatever the value U I am getting minus the exact solution, that is the error now. And our hope is that we will reduce this error as K progresses. So this UK is given by MUK minus 1 plus C, and U star is given by MU star plus C. So if I put this, then C cancels out. I put it here and I put it here. So C cancels out. I have MUK minus 1 minus MU star. That means M into UK minus 1 minus U star. So that should be my error after K minus 1th iteration. If kth iteration error is EK, that is UK minus U star, then K minus 1th iteration error will be UK minus 1 minus U star. So now I have established a relation between EK and EK minus 1. Similarly, it can be shown that EK minus 1 is equal to MEK minus 2. ek minus 2 equals m ek minus 3, so on and so forth. We can keep on doing this. Therefore, I can write this ek is m ek minus 1. M ek minus 1 is ek minus 1 is m ek minus 2. So m square ek minus 2, which is equal to m to the power 3 ek minus 3, etc., up to m to the power k ek minus k, so e naught. So e naught was our initial error. So now we have established a relation, this ek m to the power k e naught. E naught is our initial error. That is the difference between exact solution and the initial guess. All right, so now we understand the solution converges when k is large, in many iterations, this ek should go to 0, then we can say that solution converges. So theoretically, when k goes to infinity, we hope that we will reach exact solution. Then we can say solution converges. Well, then we can say that limit k tends to infinity, the norm of this mk e naught will be 0. That would be the condition of convergence. Now, that sounds good that this mk e naught 0, k tends to 0 will be the condition of convergence, but that doesn't give us much really. M is minus E inverse F, so it depends on how we break the matrix. E naught is the initial guess. It depends on initial guess. So you understand that whatever it is, if I keep on multiplying this M matrix with E naught, overall it should go toward 0 or null matrix. That's what it looks like. But then M depends on this E plus F, how I'm breaking A, but it doesn't give us much. How do I know that for certain conditions, for Gauss-Seidel or Jacobi, it will converge or not? So we'll not go very deep into the theory, but I'll tell you how we can say so that it will converge or not. Let us say that I have this matrix A is given by this A11, A12 up to A1n. Similarly, A21, A22, A2n, and AN1, AN2 up to ANn. So this is an n by n square matrix with this small a as its element. Now there is a criteria which we call Scarborough criteria, is a very famous criteria. It says that for this matrix A here, the sufficient condition for Jacobi method to converge is for each of this row, if I take this II, that means for each of this row, this diagonal element, if I take its value should be greater than or equal to the absolute value, sum of the absolute values of all other elements. So, for example, in row 1, it means that A11 should be greater than or equal to sum of A12 plus A13, etc., in absolute value. And this should be satisfied in all rows, and in at least one row, it should be greater than, not greater than and equal to, it should be greater than sum of everything else. This is a condition we call diagonal dominance. It basically says that diagonal element, if I take, that is very heavy, it is more than the sum of others. So this condition is called diagonal dominance. If this condition is satisfied, then the Jacobi method will converge. Now you see that this is the condition that is called sufficient condition. Sufficient condition means that if this condition is satisfied, we are sure that Jacobi method will converge. However, solvers which are not obeying this condition may still converge. We don't know that. This is only sufficient but not a necessary condition, but it gives us certain guideline. The proof of this criteria is beyond the scope of this course, and this criteria is strictly applicable for Jacobi method. There is no proper criteria for Gauss-Seidel, but the same criteria we use for Gauss-Seidel, and we are quite successful in using in Gauss-Seidel. And we will not go any deeper in theory that how this criteria is actually developed. That will be going deeper into the mathematics part. We will not go there. Now to summarize, we have now completed our discussion of linear solvers. This is the last part of the linear solver. And we have seen that two different types, direct and iterative. Iterative methods do not change the matrix A at all. Therefore, this method is preferable for sparse matrices which has lots of zeros. For large matrices, iterative methods are actually useful. They are much better, much more efficient than the direct method in terms of CPU time. There is, of course, another class of method and which does not come under the umbrella of either direct or iterative. So as your exercise, I'll urge you that you go and see that what kind of method we are talking about that cannot be called direct, cannot be called iterative. So what are they? Let me know if you can find out. You can post your idea in the forum. Thank you. That's all for this lecture, and I'll see you in next class.